So, I guess on Sunday, Huston gave me the title Graphs and Pathfinding for Thursday, which is really fun. And so we originally, the idea was on Tuesdays we would have like more intro stuff, so as not to bore the people who have done it before, and then on Thursdays we'd have more advanced stuff, so as not to scare off the people who have just started. So congratulations, you either didn't read that or you self-sorted yourself into the advanced class, I don't know. Hopefully it'll be straightforward enough that I will not have everybody looking at me like I'm crazy, regardless of what your background is. So I've got a couple slides in here to start. What is everybody's background? I'm assuming everybody here is like in CS at least, or like a related field, or just likes programming, or I came to the wrong room. Does anybody not know what a graph is in terms of like discrete math? Raise your hand. Okay, that's fine. Does anybody, raise your hand if you know several graph algorithms, like off the top of your head. Okay, so good spread of people here. How many people are in or have taken 3114 or combinatorics already? Or an equivalent class? Okay, that's good. If you are not in one of those, we're going to do programming stuff later, so maybe pair up with somebody in case you have questions. All right, so I have a picture here that I drew very well of a graph. Since some of you raised your hand and said you did not know what a graph is, this is about as simple as I can make it. It's a bunch of nodes, which are the blue circles, connected to each other with edges. And that's kind of it. If you take a math class, you literally represent it as a set of nodes and a set of edges that connect them. There are different types of graphs to represent different things. The one I just showed you is kind of the simplest case. We have directed graphs, which instead of just connecting to each other, they connect in one direction, usually represented with arrows. There are weighted graphs, where each edge has a weight for some reason. Depending on what algorithm you want to apply, the weights might mean different things. And so algorithms are kind of what we can do with graphs. Just like you have arrays as a data structure in computer science, and you can do many, many things on them, or you have things. Graphs can either be just part of an algorithm, or you have an algorithm that just runs on graphs. Talking really fast. So what I was going to talk about today, depending on how people are understanding me, are just traversals, which are kind of like you have an array. You go over everything in the array. You can go over everything in a graph, all the nodes or all the edges. Sometimes it's called a search, just like you can have linear search through an array to find like whatever element you're looking for. You can search through a graph to find a node you're looking for, find an edge you're looking for. These algorithms are also sometimes called tree growing algorithms. If you take 40104, professor will call it a tree growing algorithm because while you explore it, you make a tree. It's not all that important for now. But the two most common ones are breadth first search and depth first search, which are just the order in which you go through the graph. Show of hands, people who know or have heard these terms before. That's really good. Okay. Show of hands of people who can code that without looking at stuff. Even better. Okay, maybe not this section. I know you guys. Does anybody know Dijkstra's algorithm and can code it without looking it up? Okay. So I'm going to go over today mostly breadth first search, since a lot of people apparently do not know it. In the slides, there's both breadth first search and Dijkstra's, at least in terms of illustrations. I'm just going to go over breadth first search, and if people are like, wow, this is so easy, then we can go back for it. If you're too bored, you can look through the slides on Dijkstra's. So I'm going to go back to this picture. Actually, never mind. Breadth first search is a searching algorithm. Some people call it. It's also a graph traversal algorithm. And it's basically just a way to take a node and go from that node to other nodes, go from those nodes to other nodes until you either find what you're looking for, something happens, or you've processed the entire graph. So you start at a single node and you basically expand out in terms of distance. So you start at one node, distance 0. All the ones that are connected to it are distance 1. All the ones connected to those are distance 2, and so on and so forth. So I've got a picture here of just a regular graph, which you can see as letters A through E. And say I wanted to start at A, and the one thing that I wanted to find for some reason is node E. The way breadth first search starts is you would start at A. And now we're looking at A. We'll start processing A, and the nodes that I'm processing I'll mark red. And when we look at A, we can see that connected to it via those nice little lines are both B and C. And so we're going to look and call these the neighbors of A, both B and C. And we're going to add them onto this queue on the left to be processed. Okay? And once we're done with that, we can move on to the next thing to process. We'll process B. And we'll notice that it has both C and D as neighbors, but we've already seen C before, so there's no reason for us to process it again in the case of a regular breadth first search. Then we'll move on to process C, and we'll see that it also has neighbors D and E, but D has already been seen before, and we'll move on. D is the next thing we process. There's no neighbors that we haven't seen, so we don't really do anything. And then we'll finally process E, and that was a breadth first search from A to E. And that was really fast, so I'm assuming I confused a bunch of people. Did the picture help anybody? Okay, I'm gonna skip over these and basically go straight to implementation because nobody's talking to me. Anyone? Okay. I made the pictures like this for a reason because it kind of mirrors exactly what happens in algorithm. It probably doesn't make a lot of sense if you're just going from this slide where I say, start at a single node and search all neighbors. That doesn't really make sense. But if you kind of visualize it like this, you start with one node and you kind of fan out to nodes you haven't seen until eventually you get to where you want it to be, or you run out of things to look at. If there was no edge here to E, there's no way I could get from A to E via just taking one of these little step connections. So I would be done, and my breadth first search would never have found E, which is sometimes like a valid thing you're looking for. If you're just looking to see if there's a way to get from A to E and you don't find it, that's a valid outcome for your algorithm. Okay. So I went over what a graph is, which I said was a bunch of nodes and connections between them called edges. So we're here for competitive programming, which means you're going to be writing code for this, hopefully very quickly and hopefully correctly. So you're going to need to know how to at least represent this with data structures you already know. There's no, like, as far as I'm aware, if you're using Java, there's no like java.util.graph that you can use. If you use Boost in C++, there is. But I listed a couple of ways here that are kind of the standard ways of representing a graph. One is to just take all the edges you have, maybe make a class called an edge that has, like, you know, left and right of the edge, and just have an array of them, or an array list, or some collection of edges. Another way is what we call an adjacency list, where you have kind of like a 2D array of nodes. So you would have, right here I have a list of nodes. And so you would have your vertices in your graph kind of indexed from 0 to n. And then you would look inside your list and you say at index 0, you have another list. And the elements of that list are the nodes it's connected to. It'll make more sense later, hopefully. In adjacency matrix, I didn't even put anything here because it's very infrequently used. But in adjacency matrix, if you have n nodes in your graph, it's just an n by n matrix. And if, say, nodes I and j are connected, you put a 1 in the matrix at index ij. You put a 0 if they're not connected. There are other variations where you can put different things in the matrix depending on how they're connected, but that's the general idea. For most competitive programming things, speaking from experience, just use an adjacency list if you have an explicit graph with edges. In almost every case, unless you have a specific algorithm that depends on you using a different data structure. I've listed 2. Floyd-Warshall is like one of the only ones that will ever use an adjacency matrix. In Kruskal's algorithm, you're basically just processing a list of edges, so you don't need an adjacency list. The easiest way to represent it, in my opinion, if you're using Java, is something like this, where you just have an array list of array lists in the graph, and you can initialize it by just appending on an array list that are empty, and then you can connect them pretty straightforward. If you want to connect 2 nodes, assuming your nodes are numbered, which you're going to have to do in most cases, or sometimes the problem will just give them to you as numbers from 0 to n. You can connect them just by basically taking the ith index in the outer array list and appending on the number j, if your nodes are represented by integers here. For bidirectional graphs, which the pictures I was showing you are, you will also add the inverse, which this is not. This is not the inverse. That's the exact same edge. Sorry. No. It's Control F5. I was hitting Control F5 doesn't work, apparently. And the main reason that adjacency lists are preferred is that the main operation you usually want to do when you're doing draft convert graph traversals is, given your current node, what are all the ones that are connected to myself? And in an adjacency list, it's literally just for node in graph.getCurrent, because that's just an array list of the things that are adjacent to you. For other algorithms, you might need different operations, so you might want to model your graph differently. But a lot of times, you'll just need to traverse the graph, do something clever on it, or maybe not even clever, and get back your result. There are a lot of different ways to do it depending on like what problem you're doing here. You could use just regular arrays if you already know the size up front. You could use hash maps of lists if you don't want to use integers. You could use sets instead of lists if you need to check and see every time, because sets have a better contains method. But the general idea is that you just store the neighbors of each node directly in a list. How you represent the nodes is up to you. In the simplest case, and the way I hope it is, like if ever I'm doing a problem, I'm hoping that the nodes are just like numbers 0 to n, so I can just use arrays, and they're not like strings where I have to like look them up. Other times, depending on the problem complexity, you'll create your own node class or a state class or a vertex class that will hold maybe a number or a string, and then any other data you might need to process that node. So that makes sense to at least anyone. I have people shaking their head. This guy is smiling, giving me a thumbs up. Thank you. Okay. And now I'm going to go over a basic BFS structure, and I'm hoping that a majority of the time you're confused is during the problem, so I can actually have examples to explain it. The main data structures you need for this, if you haven't taken like 20 and 14 or 3rd and 14, some of these data structures you might not know, but you need a queue of nodes to process. So I'm not going to scroll up like 30 slides, but if you remember on the left side, there were nodes. I said I processed A, then I processed B, C, D in order. You basically just have a queue of things to process, and you represent that in Java just with a java.util.arrayDec or a linked list or whatever. You need a set of nodes that you've already visited, so you don't end up visiting the same nodes over and over again. And that's the only data structure you really need. At every turn, you process one node, add on any unvisited neighbors to the queue, and then process them just in a loop. You end up with something that looks just like this. Can everybody read that? I can't really tell. I'm kind of at a bad angle. If I were to have a problem that required BFS, this is pretty much where I'd start. You start by initializing your data structures. You have a queue and a set of visited nodes. You start by adding your initial node to both the queue and the visited set. And then just basically while the queue is not empty, process a node, add its neighbors. In a lot of cases, you're always going to have to add stuff to this because all this does is look through a graph and then throw away all the results. So that's not useful for hardly anybody. But a lot of times you'll be looking for maybe a goal node, or you'll be recording information as you go along. So we got a little comments here. Process the current state. Common one, check for the goal. You might not have like a necessary goal node. There might just be a property of the goal you're looking for, so do some processing there. You got a place to handle new neighbor states. So if you need to update like a distance table or something like that, you could do it here. And I've got a couple of slides on basically what I think the general usages of BFS are in competitive programming. To start off, you kind of need to know, if you look at a problem, whether or not you can even do breadth-first search of whatever graph you're imagining. And so does anybody know what the runtime of BFS is in terms of the number of nodes and edges? I assume some people do because you were in data analysis with me last semester, and I assume you passed. Anyone? Just like yell really loud since we've been talking. In terms of Big O, I've got a hint up here. It processes each node once for sure. And how about the edges? How many times does it process each edge? Okay, so it processes each node exactly once and each edge pretty much once. So the running time is pretty much, if you know what Big O is, it's Big O of V plus E. So that means it's linear in the number of nodes and edges, which is pretty good for most problems. The only thing you need to be careful of is sometimes problems will list there are, say, 50,000 nodes in this graph, and they won't give you a bound on the number of edges. And so technically, you have a complete graph where every node is connected to every other node, and you can have n choose 2 edges. And so if you do 50,000 choose 2, that's a much larger number than you could typically process in the competitive programming constraints, which is usually like 1 to 5 seconds. And the next thing you really need to know, maybe the first thing you need to know is, how do you recognize that you actually need to use BFS for a problem? The easiest case is you have an unweighted graph, like the picture I showed at the very beginning. It could be represented somewhere else. You could have an integer grid, like if you took 2014 years ago where you had to do the maze solver. That's an unweighted graph where you have nodes of the grid cells. You have an edge to the 4 adjacent ones. It could be state space exploration, which where you don't really have like a real graph that you can imagine as specific things, but it might be you have states that go to other states. Some common examples we have are like, has anybody done the Cracker Barrel problem where it's got like a triangle on the pegs? Anyone?
Oh, yeah,
Basically any kind of game, or not any kind of game, several games you can imagine where you can make one move at a time that takes you to a different state. You can also represent as kind of like a graph where each state is a node and the moves you can make are a single edge. And so we usually call that state space exploration, but it's the same as BFS, or technically DFS, depending on which way you're looking for it. You can also just use it if you need to look through every node in a graph and do something with it. Common examples are like determining if a graph is bipartite. But in those cases, you can also do what's called depth first search. I also wrote here, could be processing levels and increasing distance. So if you ever had an interview question that was like, given a tree, print out the levels in order, that's kind of the definition of breadth first search. All right, I went really quickly through that. Some people are nodding their heads, which is better than I expected. Okay. So I made a sample problem so people can test out their knowledge of this and hopefully be confused or not confused. And hopefully by the end, everybody will at least be able to write this code, whether it's by looking off somebody's shoulder or something. At least I've written it once because it gets easier, trust me. So I designed this board game. The details of the board game are not really that important. But you can imagine that the board is laid out like this, and I'm standing at this little green circle, okay? And each turn I'm gonna roll a 6-sided dice. And based on the 6-sided dice, I can go up to that many distance. So if I roll a 1, I could go here, I could go here, I could go here, I could go here, or I could stay in place. I can basically go up to 1 distance away. If I roll a 2, I can go up to 2 distance away. So I could go here, here, stay in place, here, here, or I could go all the way over here. So 1, 2. And so here is like basically all the distances. Starting from the beginning, you can assume the beginning is at distance 0. And the goal of this board game is to find the bread. And so, say I'm sitting here playing this, it could be with other people, details aren't that important. I'm growing impatient and I want to know basically how many dice rolls, minimum or maximum, it's going to take me to get to the end of this game or to find the bread. So you can see in this example, I could get really unlucky and roll a bunch of 1s in a row. And if I were, I would need 3 dice rolls to get to the very end of the maze, or the end of this really fun board game. But if I were to roll a 3 or higher, it would take me exactly 1, because I could just jump here, and then jump here. Is that making sense to everybody? Okay,